Hello everyone, I am Anu, pursuing PhD from University of Hyderabad. Today we will be discussing 18 electron rule. Normally we used to discuss different questions from different topics, but today we will be discussing 18 electron rule from starting from 2017 to 2022, and I have clubbed all the questions asked in these years and will be discussing in this particular presentation. So now I will be sharing my presentation. Hope my slides are visible. So what does a 18 electron rule says? 18 electron rule indicates that the total electron count can be calculated from a simple equation which equal to valence electron on central transition metal and the electrons donated by the ligands. This total electron count thus calculated should be equal to 18 or multiple of 18 so that a particular complex is stable. So the valence electron on central transition metal can be obtained directly from the electronic configuration, and the electrons donated by the ligands can be obtained from its structure. For example, ammonia, carbonyl, etc. has one lone pair of electrons, and hence it will act as two electron donors. This can be obtained from their structure. In this structure, we can say it has a single lone pair of electrons, and hence these are two electron donors. Similarly, if we consider H, sigma bonded H, one sigma bond is made of two electrons, and hence any sigma bond will also act as two electron donors. The next example is H. H has an electronic configuration of 1s1, and hence at any position it will give only one electron, whether it is at terminal position or at bridging position. Next common example is nitrosyl. Nitrosyl has nitrogen which has 7 valence electrons, and among the 7 valence electrons, first what nitrogen will do is that it will try to complete its octet. So it will it will accept one electron from the metal, thus completing its own octet, and then it will donate one of its electron, and hence nitrosyl in its linear form will act as one electron donor. Now, nitrosyl can also exist in bent form. In that case, when once nitrosyl has completed its octet, the extra lone pair of electron can also be donated to the metal. That means it can donate a total of 3 electrons. So, nitrosyl in linear and bent can donate 1 and 3 electrons respectively. Now, next concept is bridging and terminal position. Neutral ligands such as ammonia, carbonyl and sigma bonds always contribute same whether it is terminal or bridging position. But let us consider if a ligand L is bonded with two metal, that means in bridging position. So that it will not donate the same as in the terminal position in case of some other ligands like chlorine, which are not neutral or sigma bonds. In that case, for example, if we consider the structure of such chlorine atom, we can see that a chlorine atom has 7 valence electrons. So, first what chlorine atom will do, it will donate its 7 electron. It will have 7 electron. It will accept 1 electron from the metal and donate 1 electron from it. So, a chlorine at its terminal position will act as a 1 electron donor. Whereas, chlorine if bridging, it is called as mu. So, if it's bridging, that means chlorine has already completed its octet. So, it can donate the extra lone pair of electrons to a metal, and thus it becomes mu. It acts as a bridging ligand, and it can be called as mu2. So, if it is donating one more lone pair, then it will be called as mu3, in which chlorine will act as a 5 electron donor. So, in that case, it will be mu3. The next concept is hapticity. Hapticity means the number of atoms of a ligand that are coordinated to a central atom. It is represented by eta. So, this CP or cyclopentadienyl is a common example. CP can exist in different forms. It can donate 1, 3 or 5 electrons depending on which it is acted as eta 1, eta 3 and eta 5 respectively. In first case, the metal is bonded to just one atom of the ligand and it is called as eta 1 and the hapticity is 1. And in the second case, eta 3 means the metal atom is coordinated to 3 atoms of the ligand and hence it is called as eta 3. And in the third case, the metal atom is coordinated to all the 5 carbon atoms and hence it is eta 5. Next common group is allyl group and this can also be represented in a different manner. So here we can see metal is coordinated to all 3 carbon atoms. This is represented by the same structure like this. So here also we can see that the metal is connected to 1, 2 and 3 means 3 carbon atoms and this is called as eta 3 and the hapticity is 3 in this case. Next we can see what two methods are there, ionic method and neutral method for calculating the total electron around a particular complex. First method is ionic method in which we will consider the metal atom as well as the ligand is in their ionic form. For example, in this case cyclopentadienyl CP, we will consider it as Cp minus since as we saw in the structure earlier that it has one negative charge and hence it will have 6 electrons. So it will donate 6, since 2 Cp is there, it will donate 6 into 2, 12 electron and since Cp is in negative charge, Fe will be Fe2 plus and it will donate 6 electrons. So totally from 2 Cp it will have 6 electrons each and Fe2 plus will also have donate 6 electrons, totally giving 18 electrons. Now the other method is neutral method. In somebody asked some question. Okay, so we will go to neutral method. In neutral method, this is easy method and I would recommend this method to be followed in the future. So in this case, we need not want to consider about any charges and we will just see as it is. For example, Cp will donate 5 electrons and iron we will just consider it as Fe instead of Fe2 plus. So it will donate 8 electrons and totally it will have 10 plus 8 equal to 18 electrons. 12 plus 8 equal to 10 plus 8 equal to 18 electrons. Now the next one we will take some examples and then we will follow doing some questions. So in the first structure given here, rhodium is the central transition metal and rhodium has 9 valence electrons. So 9 into 3 is equal to 27 and it is attached to 3 carbonyl ligands. Carbonyl ligands, whether it is terminal or at bridging position, will donate same number of electrons, 2. Therefore, 2 into 3 is equal to 6. It will donate 6 electrons. Okay. Now, the next one is Cp. We can see there are 3 Cp attached and there is 3 metal to metal atom. So, how many electrons each will give? Can anyone answer? Okay, yeah, a rhodium valence electron is there and hence, yeah, correct. Rhodium is correct. It will give 9 into 3 is equal to 27. And what about Cp and the metal-metal bonds? Carbonyl, we know. Okay. 6. Oh, correct. Metal-metal bond means each metal-metal bond is consisted of 2. Since there is 3 metal-metal bond, it will be 6 electrons. Correct. And now Cp, we have seen earlier in neutral method, it will give 5 electrons. So 3 Cp means 15. Therefore, the total number of electrons will be 27 plus 6 plus 6 plus 15 equal to 54. This shows that this particular complex follows 18 electron rule. The next one is the example given here. In this, we can see the central transition metal is molybdenum. So, how many electrons molybdenum has in its valence shell? Okay, yeah, correct. It has 6 electrons. So, total number of valence electrons on molybdenum will be 12. 6 into 2 molybdenum means 12. So, then we have two types of chlorine atoms attached in this complex, terminal as well as bridging. Two chlorine atoms here are bridging and two are terminal. So, two chlorine terminal atom speeds each will give 1 electron and 1 into 2 will be 2. How many electrons bridging chlorine atoms will give? It will give 3. So, 3 bridging chlorine atoms are there and it will totally give 6 electrons. And one metal-metal bond is there. That means 2 electrons and 2 Cp will give 5 each. Therefore, 10. Therefore, the total number of electrons is 32 and thus this does not follow 18 electron rule. So, now as we have seen some examples, we can follow on doing some questions. Is it clear or anybody has any doubt? Okay, fine. So now let me tell you another type of example in which MCO7 plus, in which in such questions they will ask what is F. So in that cases we can use 18 electron rule where we can write X plus carbonyl 7 into 2 14. If plus sign is there, we have to subtract 1, and if negative sign is there, we have to add 1. So plus sign means subtracting 1, we should get 80 so that the complex is stable. So x will be equal to 5. So what will be x, value of x? Yeah, correct. X equal to 5. So what is 5? 5 will be from no, it's not manganese, it's vanadium. So because totally 5 valence electrons, no. So it will be from the vanadium group. So don't get confused with the number of valence electrons. It will be better if you write the elemental like periodic table initially itself before starting the paper, so that it will help you not to get confused between the metals. Otherwise, when we are writing gate answer sheet, we will get confused and might make some mistakes which are usually obvious, but because of that which we will lose our marks. So I would recommend that please write it and then you will find it properly. Now let us start question. The first question is from 2017, question number 12. The hapticity of cycloheptatriene C7H8 in MoC7H8Cu3 is. So this also can be calculated from 18 electron rule. This is the structure of C7H8. So in this we can see the metal atom can be maximum attached to 2, 4, 6 plus 1, that equal to 7. So it can donate maximum of 7 electron. Maximum hapticity is therefore 7, eta 7. But in this particular complex, in order to follow the 18 electron rule, what is the hapticity? That is what we have to find. So we know the total electron count equal to valence electrons on central transition metal plus electrons donated. Here the central transition metal is equal to molybdenum and the valence is 6 and there are 3 carbonyl ligands. So each carbonyl is 2 electron donor and hence totally it will donate 6 electrons. Now let us assume C7H8 is giving X number of electrons. So therefore this indicates that 6 plus 6 plus X should be equal to 18. That means x equal to 18 minus 12, that equal to 6. That means the hapticity equal to 6. Is it clear? If it is clear, then I will move on to the next question, or if any doubt is there, you can ask. Shikha, it's actually the maximum number of hapticity is 7. It can donate 1 or 3 or 5 or 6, any number of electrons. So for example, if it donate like this, it will be 7. But if it donate only the first 2, it will be 2, second 2 also 4, third 2 also 6. So that the total number of electrons can be 6. The maximum is 7, but it can donate any number of electrons based on how many atoms of the ligand the metal atom is attached to. So the hapticity can differ, as well as the number of electrons donated by C7H8 can also differ in each complex depending on how much it should give, so that the complex will follow 18 electron rule, so that the complex is stable. Is it now clear? Okay. So now I will check the chat box if anybody has any doubt. Okay, I think it is clear for everyone. Now we will then move on to the next question. So the next question is from 2018, question number 23. The total number of valence electron in tungsten eta 3 Cp, eta 5 Cp, CO twice is atomic number of tungsten equal to 74. So here we know the atomic number, and hence we can know the valence number of tungsten, the central transition metal, which in this case is equal to 6. Each carbonyl is a 2 electron donor, and carbonyl will give, since 2 carbonyl atoms are there, we know 2 carbonyl atoms will give 2 into 2 is equal to 4. So how much Cp will give? There are 2 types of Cp here, eta 3 Cp and eta 5 Cp. How much eta 3 Cp will give? Eta 3, correct, 3, and eta 5 Cp will give 5. So the total number of electrons will be 6 plus 4 plus 3 plus 5, that equal to 18. So the total number of valence electrons in the complex given will be equal to 18. So this is based on simple 18 electron rule. If we know that, we can answer any such kind of questions. So is this clear for everyone? Okay, fine. So then we can move to the next question. The next question is from 2019, question number 30. The product obtained in the reaction of Mn2CO10 with Br2 is. 4 options are given. So we can find out what is the correct option. First of all, we can find out what is the structure of the complex given in the question, Mn2CO10. So in order to find that, we can use the help of 18 electron rule. The central transition metal manganese is having a valence number of 7 electrons. Since there are 2 manganese atoms, total of 14 electrons will be there in the complex. And carbonyl is a 2 electron donor, and 2 into 10 will give 20 electrons. So therefore the total will be 34 electrons. In order for a complex to be stable, we know it should have 18 electron rule it should follow. That means it should have 36 electrons. So it is short of 2 electron. That 2 electron can be obtained from 1 Mn bond. Therefore, the structure will be like this, where one MN-MN bond is there and 5 CO ligands is attached to each manganese central metal atom. So now in this complex, when we add bromine atom, different types of reaction can happen. So in this particular case, there are three different options. Option A is MN-MN bond can break. Okay. Then option B is one Cu can be replaced by the bromine, and C is both of this can happen. That means both MN-MN bond can break and also there can be replacement of carbonyl. First of all, let us go through the first method in which MN-MN bond is breaking. So if one MN-MN bond is breaking, that means one bromine atom will be added. So therefore we will get MnCO5Br. That means one MN-MN bond is equal to 1 electron. So bromine is also a 1 electron donor and Mn will be added to 1 bromine. So thus we will get MnCO5Br, and totally 7 plus 10 plus 1 equal to 18 electrons. So such a compound will be following 18 electron rule, where Mn is attached to 5 carbonyls as well as 1 Br atom. Now the second option is where a carbonyl can be replaced. So in such a case, a carbonyl is a 2 electron donor and bromine is a 1 electron donor. So in order to replace one carbonyl, 2 bromine atoms should be attached. So the complex thus formed will be having a formula Mn2CO9Br2. So such a complex will be formed in through way 2 in which carbonyl is replaced. The third method in which both of the things happen, that means both MN-MN as well as carbonyl is replaced. In that case, we can see that the carbonyl will be replaced by 2 Br and the MN-MN bond will be replaced by 1 Br. So total of we can get a 3 Br will be attached to Mn. So 1, 2, 3, 4 carbonyl as well as 3 Br. MnCO4 Br3. So the correct option is MnCO5Br, which is obtained through the way 1. The no other option is matching with the answers obtained for us through option B and option C. So in the second option we can see that one carbonyl, if it is 2 carbonyl is replaced, means 4 Br should be added. So the option B is wrong. In third case, one carbonyl is replaced, that means 3 Br should be there, and in the last case 1 carbonyl is replaced, so 2 Br should be added. Therefore, all other third 3 options are wrong and the correct option is option A, MnCO5Br. Clear? Yes, ma'am. Okay. So this question can be solved in another method also. This is a method where we solved from the question we solved and derived into an answer. Another method is that from the answer from the options itself we can get into an answer. This can be done with the help of 18 electron rule, where we will find out the 18 electron, whether each option follows 18 electron rule or not, and then we can understand which one is the correct option. For example, option A is MnCO5Br, in which manganese is having 7 valence electrons, carbonyl is 2 electron donor, and hence 10 because 5 carbonyl is present, bromine is 1 electron donor, therefore the total electron count will be 18. So MnCO5Br follows 18 electron rule. The next example is Mn2CO8Br2. Mn, since 2 manganese atoms are present, 2 into 7 is equal to 14 electrons it will donate. And the second one is carbonyl. Carbonyl have 8 carbonyls are present Since therefore 16 electrons it will donate, and bromine will donate 2 electrons. And since one Mn bond is present, as we have seen earlier, 2 electrons it will donate, and therefore the total electron count will be 34, which indicating that the option B does not follows 18 electron rule. Now option C is MnCO4 Br2. In this case, we can see the central transition metal manganese has 7 valence electron, 4 carbonyl is present, therefore 2 into 4, 8 electrons is donated. Each bromine will give 1 electron, 2 bromine is present, so 2 electron, and therefore the total electron count will be 7 plus 8 plus 2 is equal to 17 electrons. This also do not follow 18 electron rule. So this is wrong option. The next one is D, Mn2CO9Br. Mn 7 electrons, so 2 Mn 2 into 7 14. And the second one is carbonyl. Carbonyl has 9 electrons and 9 carbonyl 18. Bromine has 1 electron. 1 Mn bond will give 2 electrons, and therefore total electron count will be 14 plus 18 plus 1 plus 2 equal to 35. So this also does not follow 18 electron rule. So among the 4 options given, the only option that follows is option A, MnCO5Br. Hence, therefore, the answer to this question is option A. So is it clear? I'll check the chat whether you guys have asked any questions. Okay. So I guess it is clear. Okay, clear, fine. Now let us move to the next question. Question number 31, GATE Chemistry 2019. The molecular representation of WCP twice CO twice is. CP is cyclopentadienyl. Such a question can also be answered directly from 18 electron rule, since we have studied what is hapticity of CP. CP can exist in different methods, eta 1, eta 3 and eta 5. So the compound complex given is WCP twice CO twice. So in this, this complex should follow 18 electron, and tungsten is having 6 electron. Carbonyl, 2 carbonyl is present, 2 into 2 is equal to 4, and the compound to follow 18 electron rule, we should have 6 plus 4 plus 2 into x. Let x be the number of electrons donated by Cp, should be equal to 80. Therefore 2x should be equal to 8. How can Cp give 8 electron? Like in what way Cp will be present? Anybody? Yeah. No. 4 actually, we have seen earlier how Cp. No. Cp has 2 plus 2 plus 1, 5 electrons. So if metal is attached to one carbonyl atom, it will be eta 5. And if metal is attached to 2 plus 1, that is 3 carbonyl atom, 3 carbon atoms, it will be eta 3, and in if metal is attached to 5 carbon atoms, it will be eta 5. So it will donate 1, 3 and 5 electrons. It cannot donate in between 2 or 4. It cannot donate. So 8 should be divided in terms of 1, 3 and 5, and eta will exist. How can it exist? So that it will be divided between 1, 3, 5. Yeah, okay, correct. It will be eta 3 and eta 5. So the correct option is option C, tungsten eta 3 Cp, eta 5 Cp, CO twice, where Cp exists in eta 3 and eta 5 hapticity. Is this clear? Okay. For further reference, you can visit NPTEL site and the YouTube link is given here. So I hope this one is also clear. Whether any doubt, you guys have any doubt? Okay, so this is a question from 2022. In this first two examples we did as an example. So the next two also we will do now, and we will see that whether this one follows 18 electron rule or not. So the first example, the total number of valence electrons on iron. Iron is the central transition metal in the first example. So iron has 8 valence electrons. So total number of electrons donated by iron will be 8 into 2 is equal to, 16. Correct. Now how many carbonyl atoms are attached to this complex? 2. Correct, 2. So, carbonyl, whether it is terminal or bridging, it will donate same number of electrons, right? So, there are 2 carbonyl ligands. So, how many electrons it will totally give to this? 4. Okay. Now, chlorine. How many chlorine atoms are present? 2. Yeah, correct. And 2 terminal means 1 electron each. Correct. So, 1 into 2 will be equal to 2. And how many metal-metal bond? 1. So, 2 electrons. And how many Cp? 2. And each Cp will give 5 electrons. So, totally it will give 10 electrons. Therefore, the total number of electrons will be 16 plus 4 plus 2 plus 2 plus 10 is equal to 34. So, whether it follows 18 electron rule or not? Yeah, correct. It does not follow 18 electron rule. It should have 36 electron, then only it would have followed 18 electron rule. Okay. The next example is given here. In this example, osmium is the central transition metal which has 8 number of valence electron. One chlorine is attached, one benzene is attached, then nitrogen 2N is attached, one in linear fashion and one in bent fashion. So, how much this will give? We can see one by one. Osmium will have a total of 8. Terminal chlorine will have 1. Benzene will have 6. There is no confusion. Linear N and bent N, as we have seen earlier, it will give 1 and 3 respectively, and the total number of electrons will be 18. And thus, this follows 18 electron rule. Oh, one negative charge is also there. So, we have to minus one negative charge and then we will get 18, and then this follows 18 electron rule. So, is this clear or should I explain this again? Okay, Anand. Actually, we have to see how nitrogen is attached. The geometry is important here. How nitrogen is attached to the osmium. That is important to find out which one is linear, which one is bent, how it will donate. The other ligands are easy. How chlorine and other ligands will give, that is easy to understand. Correct? That you understood, no? Okay. Now we will see how N is there. So one we can say is directly attached to the osmium. So that will act as a linear N. And we have seen earlier that linear N will have how many electrons it will donate? 1 electron. And in the next one, this will be attached in this fashion at 120 degree each other. That is called as bent nitrogen. So when a nitrogen is attached to the osmium in bent fashion, we have seen earlier that it will donate 1 plus 2, that is 3 electrons. So it will donate 3 electron and it will act as a 3 electron donor, and whereas in linear case it will act as a 1 electron donor. And positive charge means we have to subtract 1 as we have seen earlier, and hence the total number of electrons will be 8 plus 6 plus 1 plus 1 plus 3 and minus 1 due to the positive charge of the complex equal to 18. So is it clear? This follows 18 electron rule. This one is now clear. We can see the nitrogen attachment that we have showed in the earlier slides. One second. So here we can see, no, this nitrosyl is attached in a linear fashion to the metal, where nitrogen is giving one electron and acting as a one electron donor. So whenever nitrosyl is attached in linear, it is one electron donor, and in the second case nitrosyl is giving 1 plus 2 equal to 3. So in that case nitrosyl act as a 3 electron donor when nitrogen is in bent position. So this much is clear. Now I hope this is clear. If still it is not clear, you can ask me again. Okay, fine. So in whole whatever we have discussed today, if you have any doubt or anything is not clear, now you can ask, because only in this platform you can ask questions directly.